Well, today I want to talk about painting in polarization. I would say it's basically a new medium for, I mean, you could call it art, but basically for representing colors and shapes, and hopefully you'll see both the opportunities that are presented by this medium and also the gross challenges, how this medium of painting in polarization, and in particular, creating art with transparent Scotch tape, basically, is challenging my conception for what I can do artistically, and how do I work in color spaces that I'm unfamiliar with. And I think you're going to find this this interesting. Now, normally I would give a lecture about physics and light and polarization and how, what it all means and what the fundamentals of it are, but that would take a course, and also it would be highly technical. So what I thought I would do today is we'll watch a couple of YouTube videos, brief ones that introduce the notion of polarization and light. And then I'll have a little bit of supplemental material from me that will get us up to, like, catch us up to get us on the same baseline for what we're talking about before I show you what it actually looks like in practice to paint with polarization. So I don't know if you can hear YouTube videos through the screen. Let's see.
Hey guys, I'm Kevin, and today...
Can everybody hear that?
It sounds good to me, Aaron.
Okay, I'll keep going.
I'd like to share with you some of my favorite experiments, and they have to do with polarization. So what exactly is polarization? Well, light is an electromagnetic wave, and so it has an electric component that oscillates, that goes up, comes back down, and keeps doing that as it moves through time, and also as it moves through space. But it's electromagnetic, so it's got this electric component, but it also has a magnetic component, and this does the same thing. It oscillates up and down and back. Now, they go together, and so we have they go together in a very particular way. In fact, the magnetic component is exactly perpendicular at right angles to the electric component. So it looks something like this as it's going through space. So you can see the magnetic and electric fields oscillate together and are out of phase. So this light is linearly polarized because the electric field just goes in one direction. It goes straight up and down. Now, if we're, say, like this, that's going to be vertical polarization. And we move it this way, we call that, horizontal polarization. Now, light doesn't have to be just vertically polarized or just horizontally polarized. It can be anywhere in between. Light sources that produce light that's polarized all over the place is what we call unpolarized light. So this is a flashlight, and it's going to produce unpolarized light. And I can demonstrate this for you by using a polarizer. So this polarizer here is labeled axes, and it has a little arrow, and that shows you which way it lets through, or which polarization it lets through it. So the first thing you notice is that this is somewhat dimmer than the background, and that's because it's not letting all the light through it. It's only letting the light that's polarized, in this case, with the electric field horizontal. So if we look at our light source through this, it's dimmer, but it's still there. Now we can rotate it around, and again, light's still getting through. So we have light that's getting through that's both vertically polarized, horizontally polarized, and everywhere in between. Now, if we expand this, we take another polarizer, it's just the same. Again, now we've got the axis horizontal. We can have light pass through one polarizer and the other one. So if we put them this way, you see all of the light gets through. And that's because after it goes through this one, it's horizontally polarized, and that horizontally polarized light gets through, makes through the second one. Now, if we rotate these so that one of them is perpendicular to the other one, now all of a sudden, no light's getting through. And that's because the light that comes through this one first, let me show you how these are set up like that, is all horizontally polarized, but this one only lets through vertically polarized light. So as a result, no light gets through. Do this with our flashlight again. Now, I said we're going to use polarized sunglasses. So first of all, let's find out how they're polarized. We're going to use one of our polarizers that we know which way it's polarized. And put it here in front of the light. That's producing horizontally polarized light. And we can start with our sunglasses, start rotating them around. You can see the light makes it through. There it gets pretty dim. Starts getting brighter again. That's maybe the brightest. And then back around. So it's dimmest right about here. So which way does that mean that the sunglasses are going to have to be polarized? That's right, vertically. So we can go ahead and mark our sunglasses as vertical polarizers here. Now, let's do something interesting. So we have our sunglasses. We have our initial polarizer here. This is horizontally polarized. Sunglasses are vertically polarized, more or less. There we go. I think that's the best I can do. What happens if I use another polarizer, but I stick it in instead of, well, if I stick it in horizontally, it's about the same. If I stick it in vertically, well, it eliminates that light there. What happens if I stick it in an angle? Let's find out. Oh, actually gets brighter. That's interesting. What's going on there? So that was kind of interesting. What's going on there? Well, let's take a look at it step by step. So we have our flashlight first, which produces unpolarized light. So we've got some vertical, some horizontal, side to side. And then we pass it through a polarizer, which only lets through horizontally polarized light. Then if we had what we call the analyzer, the sunglasses, just vertically polarized, that would block all the light. But we don't. We have this other polarizer set at an angle. So when this light arrives at the polarizer, it's horizontally polarized. I'll draw that as a black line here. But then the polarizer is at an angle, like this. So that's going to let through light that's at this angle as well. And so some of this light that arrives at it is going to get repolarized along this diagonal. Now similarly, we come to our analyzer, a pair of sunglasses here. They're polarized this way. The light that arrives is diagonal. And again, there's some component of that that is now vertical, and that makes it through to our eyes. So that's now why we see an increase from what was previously zero light there. Well, that's kind of neat, but you could be asking yourself, is there an application for this? And there sure is. It's in liquid crystal displays. So the way a liquid crystal display works is it has a back pane that's illuminated from the source behind it. This pane is polarized again, and it has a front pane on it that's cross-polarized. So normally, no light gets through. However, what they do then is they put in some liquid crystal. What that liquid crystal is this kind of rod-like material, and it aligns itself naturally here with the polarization axis, and then it rotates slowly up to this front analyzer axis. So in that case, what we actually have is, as it's rotating the light with it. So it's as if we were having this angled polarizer in there, and we're getting some light through. When we apply a voltage, though, the rods, they all shift, and so they go flat. And it's as if we removed it, and we get something dark. So where do we use LCD screens? Pretty much everywhere. We have them on our calculators, and of course, also on our computers. So here, I pulled up just a blank PowerPoint slide, and I'm going to show you that the monitor, the light coming out of the monitor is polarized because it has that final analyzer on it. So we've got our polarizer here, put on our polarized sunglasses, and we can rotate them out, and you can see that indeed block out most of the light, and it comes back. So the light coming out is polarized, and that's actually pretty well polarized too. So we'll leave them on, and let's do something cool with this. Actually, I'm going to take this off for a minute to show you. We're going to look at the stress in this Petri dish. So if we just look at the Petri dish, then, yeah, I mean, it looks okay. We kind of maybe see something at an angle. If we put on our analyzer, and then look at the Petri dish, whoa, now we get a bunch of bright colors. What's going on there? Any ideas? As the light is passing through the Petri dish, it's getting rotated just as it was passing through the rotating liquid crystal. And that lets more and less light through. And since the Petri dish is very uneven, And even some areas of it pass through, for example, more red than blue, and that gives us this nice rainbow effect. It's also very striking, of course, if we rotate the analyzer, so we're not seeing a whole lot of light, and then we put it in there too. Now, if you're wearing...
Okay, so you might think that was a fairly low quality video. Let me assure you that the much higher quality videos would all be approximately an hour long and have half as much of the content of that video. So I actually rather like that video there. I have another very short video that basically says the same thing. This is extremely short, and it really gets us on base with what we want to talk about today.
Here's a single sheet of polarizer, a kind of filter that lets through only electric field vibrations that are in a certain direction called the transmission axis. I've marked the transmission axis on the polarizer with that double-headed arrow. Vibrations perpendicular to that are blocked, absorbed by the material. This polarizer is in front of a light table, and the light waves coming at you are wiggling up and down, left and right, and every diagonal direction. Those diagonal vibrations, however, can be thought of as simultaneous vertical and horizontal vibrations. So we can think of the light as having only vertical and horizontal components of vibration. And this polarizer, as it's oriented now, is letting through only the vertical vibrations. If I turn it, however, then the light getting through is now vibrating horizontally. Here's a second polarizer. With the two transmission axes parallel to each other, there's not much difference where they overlap. The first filter, closer to the light source, blocks almost all of the horizontal vibrations and lets through the vertical vibrations. The second one, closer to you, lets almost all the vertical vibration through. It would block horizontal vibrations, but there are no horizontal vibrations hitting it because they were blocked by the first polarizer. Now, if I rotate the foreground polarizer, what will happen? Let's see. The first polarizer blocks the horizontal vibrations. The second blocks the vertical vibrations. So essentially no light gets through. I say essentially because the filters are not 100% perfect. Now I'm going to put a horizontal polarizer on a stand here in the foreground. So I have a hand free to introduce a third polarizer, a small one, in between the first two. Notice that some light gets through when the small polarizer is diagonal, but no light gets through when the small polarizer is either vertical or horizontal. Can you explain why?
Okay, so let me see what I got here. Okay, so those videos were basically introducing the idea of polarization, that we like to work with linear polarization. And what linear polarization means is that the electric field that makes up light is aligned in a particular orientation, and it's only aligned in that direction. And a polarizer is basically just a gate. It allows light that's with the electric field aligned in a particular direction, in the direction of that polarization gate. Now, you saw in the videos that when there's another polarizer in between the cross polarizers at some angle, that it then does let some light through. So it goes from a zero condition of light to some higher condition. And you might be curious about why that works, but also quantitatively, how does that work? And so quantitatively, the way a polarizer works is what's known as Malice's law, which is one of the favorite laws of physics students because it's actually fairly simple. And that's that the transmitted light through a polarizer, I, the transmitted intensity, is given by the incident intensity times the square of the cosine of the difference between the orientation of the incoming light and the polarizer. So if the polarizer is at 90 degrees to the orientation of the incoming light, then this theta light minus theta gate is 90 degrees, and the cosine of 90 degrees is 0, and the cosine and the square of 0 is 0. So you have no light transmitted. But if you're at some other angle, let's say 45 degrees, the cosine squared of 45 degrees happens to be 1/2. So when you have cross polarizers, no light comes through. But if you were to uncross them by 45 degrees, half of the light would come through. And what this means is that as soon as you leave from the cross polarization condition, even by a few degrees, more and more and more light comes through the gate until you have, let's say, light polarized that's been rotated and is coming into the gate at the same angle as the polarizer, and then it's the cosine squared of 0, which happens to be 1, and I is equal to I naught, which means the transmitted light is 100%. It's equal to the incident light. And so the rotation of polarization between polarization gates is a control knob to some extent for the intensity of light that can emerge through these gates. So I need to introduce, we talked only about polarizers, which are gates, but there's another important concept known as birefringence. So this is a fancy word that you can use around your friends to make them think that you're smart. I don't recommend doing that because the concept of birefringence is actually kind of complicated, and until you've got it down, don't embarrass yourself like I've embarrassed myself before. A transparent material that has a different index of refraction along different directions is birefringent. What that means is that basically optically the material looks different to the light depending on its orientation. Along one direction and another direction of polarization, the material looks differently to the light. What this means is that depending on the magnitude of the difference between the indices, that means depending on how birefringent this material is, and depending on the thickness of this sample, how much opportunity it has for displaying the difference in this index of refraction, the material can be used to rotate polarization. And so this is kind of similar to having a polarizer, but it's a little different. Instead of a gate where a polarizer kills, you know, according to the cosine squared law, the polarizer kills anything that's not aligned with it, a birefringent material can be used to rotate the polarization. So if you put a birefringent material between cross polarizers, depending on how birefringent that material is, it can simply rotate the polarization away from that cross condition and allow light through. So birefringent material rotates polarization, and that's the key for what I'm going to show you. Okay, so this is just a visual example of what I just said. Let's say we start from the left and we have some white light. Let's say we start from the left and we have some white light. White light is unpolarized. It's got electric fields pointing in every which way. It hits the first polarizer. In this case, the polarizer is drawn such that it's a 45-degree gate. And what emerges from the polarizer is just light at 45 degrees. That light, and light at 45 degrees, your eyes can't tell what that looks like. It looks like light. It just means that the electric field is oscillating at 45 degrees to the horizontal. And, you know, my understanding is that there are some creatures in nature that can tell the difference. They can tell what polarization something is, but we can't. We can't see polarization. We just see some intensity of light coming through the polarizer, but the light is, the electric field is oriented at 45 degrees. It then hits this object. It's called an anisotropic crystal. That doesn't matter. It's a birefringent material with some thickness T down here. And you can see it says N1, index 1 is vertical and index 2 is horizontal. So this material has two different indices of refraction. And the light coming in is at 45 degrees. So it's experiencing some of N1 and some of N2. And what that results in, and the details don't matter until you take a fourth-year optics course with me, that will rotate the polarization of the light. And in this case, they've drawn it so that it rotates the polarization vertically. So what's coming out from this plate birefringent material, and in the next minute, this plate is going to be a piece of Scotch tape. It will rotate the polarization, and now it's going to be vertically polarized. But unlike a gate that will kill off some of the light based on the cosine square of the difference, in this case, it would be, if this was a polarizer that was vertical instead of a birefringent material, half of the light would come through it. But now it simply rotates 100% of the light to become vertically polarized. It then crosses this analyzer. The analyzer was crossed with the polarizer. You'll see the polarizers that say positive 45 degrees. The analyzer is at negative 45 degrees. So if the birefringent material wasn't there, no light would get through. But now the birefringent material rotated the light to be vertical, and some of it gets through. And so that's how birefringence works visually. Now, that figure said, you know, birefringent crystal or anisotropic crystal. Are there any other like everyday materials that work like this? And the answer is that there's ton. You saw in the first video on YouTube that just a plastic petri dish works that way. Almost all of your plastic materials will be slightly birefringent because the way that they were made, there were some stresses put into them. And when they cooled into the shape that they're in, those stresses got locked in, and those stresses affect the indices of refraction, and you get some kind of stochastically birefringent material. What that means is it's randomly birefringent. And that's why when you take a look at the petri dish from the video, it had colors in all kinds of shapes and directions because the birefringence was unpredictable in some way. One material, a real material that's birefringent in a very organized way are Scotch tape, cling wrap, many other plastic films are birefringent in a very organized way, right? Why are they organized? Well, these plastics are actually made by stretching, right? They're made of polymers, and then they're stretched in some orientation. And the reason they're stretched in a particular orientation and then cooled and locked in that orientation is it gives them mechanical stress. So Scotch tape, 3M packing tape, all of these, even cling wrap, are birefringent, but that's just something that happens coincidentally. The company doesn't care about the optical properties of these, the polarization properties of these tapes. They're made for mechanical strength, but fortunately also it locks in birefringence to these materials, right? And then this is another subtle point that I had not appreciated before I started this project. Most interesting, and what's going to give us all of what we're about to see, is that the birefringence in these materials actually depends on the color that goes through them. So every color that goes through them experiences a different birefringence and therefore rotates slightly differently. And that's why we're going to have some white light, and we're going to rotate different colors differently using Scotch tape. And then we're going to put a polarizer to block certain things that became crossed with that. But other wavelengths are going to come through. And so we're going to get certain colors coming through while other colors not coming through. And this is conceptually quite complex. If you're utterly confused at this point, do not worry. Probably I'm the only one not confused at this point. If you are not confused at that point, don't worry. You probably do understand I'm an awesome teacher. So both are fine. But you don't have to understand. So everything I told you was basically the background so that you might be able to understand what you're about to see to some extent. And if you decide to play at home with this, you have some idea of what you're doing. But you don't actually have to understand the fundamentals of birefringence to play with birefringence and to paint with polarization. So let me show you a demonstration. I don't know if I can do this. We're going to give it a try. What I'm going to show you is that a glass plate is isotropic. That means it has no preferred orientation. That means the light that goes through glass, no matter how the glass is rotated, the light sees the same thing. So it's not birefringent, and it will do nothing to the polarization of the light. I'm then going to show you that tape is birefringent, meaning a piece of tape can rotate the polarization in the same way or in a similar way than that polarizer that the demonstrators put in between the cross polarizations before. More layers means more rotation, because we saw that the birefringence depends on the thickness. And so by layering the tape, you're simply getting more birefringence, more rotation, which means different colors are going to be thrown in and out of this gate. And then one cool thing, if we want to think quantitatively and quasi-mathematically, is that, as you saw in the birefringent material, we had N1 in one direction and N2 90 degrees to it. That means that if you rotate a birefringent material by 90 degrees, it acts as the opposite birefringent material to before. What that means in our case is that if I put a piece of tape at one orientation and it creates some colors, if I put another piece of tape that's identical to it at 90 degrees to it, it will undo that effect. It's a plus and a minus. And so you can think of of some orientation as being some birefringence, and 90 degrees to that, it would be the opposite birefringence. So if I put two layers of tape crossed at 90 degrees, I will get some effect and then undone. And I'm going to try to show that to you right now.
Aaron, can I interrupt for a moment?
Please.
Well, a student has a question in the chat.
Yes.
And he asks, is this the same way crystals work?
Absolutely. This is so usually when you study birefringence in high school, or maybe you have an optics module in a physics course and they talk about indices of refraction and birefringence, they will show you a calcite crystal, because those were the first that were discovered to have this effect. The vast majority of research on birefringence has been done with crystals, and in fact, almost all technological usage of birefringence relies on crystals. Recently, in the last 30 years, what has made a breakthrough in our technological usage of birefringence has been with liquid crystals. You heard one of the demonstrators talk about liquid crystals. Liquid crystals are basically, they're the same as crystals. It's just that you can rearrange the molecules in the crystal any way you want with voltage in a liquid crystal. It's a liquid, and then you put a voltage and it aligns in a particular way, and you put a different voltage and it aligns in a different way. So a liquid crystal is a changeable crystal. And that liquid crystal displays are in your calculator. They're what your monitor is made of. And so actually, they're a different kind of crystal. They're a liquid crystal, but absolutely, this is how crystals work. There aren't many technologies that use birefringence in Scotch tape, mostly because they haven't been studied, and also because they're probably not as controllable. The birefringence is not as controllable as it is in something like a crystal, but that's exactly the same thing as the birefringence. That if you know about crystals, the tape itself is a kind of crystal because it's got polymers aligned in a particular way. Okay, now let me see what happens if I share my webcam, my second webcam. Okay. Let's see. So I'm now pointing my second webcam at a computer monitor. This is my an HP monitor, and it's set to a white screen. Now the HP monitor is made with liquid crystal displays. So that light coming out of there is polarized. Can everybody see that it's polarized? The answer is no. You can't see that it's polarized. Your eyes do not see polarization. Now I have a film polarizer right here. And you see nothing. You see a little bit of grain, but that's just the camera and little things. What this means when I put a film polarizer is either the screen was not polarized, or my polarizer is at the same angle as the screen. Now, it's not really working very well because my webcam is capturing everything behind it, but you can see that you can't see the screen. As soon as I cross it, it's so dark that the webcam readjusts its settings and decides to show you the triple reflection off this sheet. So a real big difference between transmitting and completely blocking, and then you can see how bright the monitor gets in the non-blocked parts because the webcam is trying to compensate for the brightness. Okay, so what else I can do is I can make a double polarizer, in that I will now leave that vertically polarized. Let's say I'll take another sheet acting as a gate, and now this sheet is aligned with the same polarization or crossed polarization. And the reason I'm showing this is I wanted to cross these polarizations for you, right? In this case, they're crossed. You just see me behind the screen. Physicists are not magicians, so we like you seeing the wizard behind the screen. Here's a glass plate. It does nothing. Even if I put the polarizer there, it does nothing. If I turn the polarizer so that it is blocking everything, you can kind of see this, the glass behind you. Shouldn't really see anything, but it doesn't do anything. The glass itself doesn't do anything. But what I can do is I can take a piece of Scotch tape. Here's a piece of Scotch tape, and I'm just going to put it at 45 degrees on that glass. Now I put it at 45 degrees because I already know that the birefringence of that tape is at 45 degrees, or is aligned with that the birefringence is aligned with the tape. So I want to rotate away from the vertical or the horizontal, so I put it 45 degrees, and then I can take my film, and by covering it, the tape is doing something. There's the blocked, and it's so whitewashed that you can't see that it's yellow. You see it for a second before the camera adjusts. And so what you're seeing here, for example, is the gate is open, meaning the screen is putting vertical polarization. The analyzer is letting in vertical polarization. The glass plate is doing nothing, but the tape is now rotating some of the light away from vertical, such that when it hits the second polarizer, this cosine square extinction happens and some of the light is removed. Furthermore, and most interesting to me, is that this is happening differently to different colors. Different colors are getting rotated and are getting extinguished by the second polarizer. And so now they're leaving out, what's probably happening is that the one layer of tape, so what you're seeing is you're seeing a one layer of tape, and then I folded the tape over so that I can pull it off. And so the red, or the I don't know how it appears to you, maybe salmon, that salmony color is two layers of tape. So what you're seeing here is rotation due to one layer and rotation due to two layers. And the blue looks like blue, likely because the red has rotated and been killed by the polarizer, and the blue hasn't rotated as much, and that's what's left. And so the color theory of why you're seeing the color you're seeing is very different than it would be with paint, for example, where oh, I'm adding blue. In this case, I'm removing some kind of red. Now, what I wanted to show you is, here's another piece of tape. Here's another piece of tape. I'm not gonna, what I'll do is there it is between the polarizers. It's, again, one piece of tape and it looks kind of identical. If I put it over the other one, it's 2 layers of tape, and the color is the same as that 2-layer of tape tab at the top. If I put it on top, I don't want to put it down yet, but if I put it on top, you can see that the 2-layer that was salmon is now yellow because it's rotating more and different colors that get killed, but they get killed by the gate. And what I really wanted to show you is at 90 degrees, I've essentially undone the rotation of the first piece of tape, right? Because the first piece of tape was this way, the second piece of tape was that way. So the overlapped part is 1 minus 1 is 0, and the other parts, they're not 0 because they're not overlapping. And so this gives all kinds of opportunities. Okay, that does nothing. Why does this do nothing? Because it's vertical, and the polarization is aligned with the tape, so the tape doesn't have an opportunity to rotate anything. So that was a mistake. Okay, so that was essentially a demonstration of what this looks like in practice, and how you can rotate and unrotate by adding. Somehow I add the opposite angle, not the opposite tape. I didn't take tape away, but now you're painting with angles and with thicknesses. Are there any questions right now? I'm going to keep going. I got Jessica. I see that there's chats, but I can't look at them while I'm running. So if you want to pass anything, you feel free. Okay. Okay, so when I first started this, this is the kind of thing I got. Now this is just random layers of tape put on a piece of glass, layered and layered and layered. You get these kind of square hatchings when tape is just slightly off from itself, overlapped, and slightly overlapped the other way. There's no way to get a circle like this unless you cut out a circle from the tape. So I cut out a circle from the tape. And this is the kind of stained glass, like art that people have been making for a while with Scotch tape. And if there was no polarizer, this would just look like a dirty pane of glass with all kinds of tape pieces on it. You wouldn't even be able to tell that they're there. You put it between cross polarizers, or in this case, actually, they're not even crossed. They were open, like in my demonstration just now. And you get such a wide variety of colors and such a dynamic interaction. And anybody can do this easily. All you need is a monitor and a polarizer. And luckily, as you saw in one of the videos, polarization sunglasses are adequate. They're 20 bucks at Walmart. I've created more of these over, playing around, and you can make all kinds of random things. And it's actually the one on the left was from my 9-year-old, and the one on the right is from my 15-year-old, because we were in lockdown, and that's why all of this started, is just trying to make some curriculum that's not being on screens. So we thought, okay, this is being on screens. Let's just put a bunch of tape on our screen and see what happens. Okay, one of the things that I made early on, I wanted to make something that was a little more dynamic. I started making some pieces that I named. This one was designed in advance. Not everything was designed in advance. The solid objects were designed in advance. This piece is called Stained Glass with Objects. One of the ideas was to show these two rectangles that are 45 degrees are basically the same, only you can't tell that the tape is layered differently in them, and therefore they give, one gives a pink and the other one gives a, I don't know, a cyanish mossy green. And so I started making more interesting things, at least aesthetically for me. And I started thinking about deterministic color. Can Can I pick the color? Can I now paint with polarization rather than randomly? Can I do something deterministic? Here's a video that explains a little bit about what I already said that I made and that tells you a little bit about color addition. I don't know if we need it by now, but I made it. We might as well watch it.
For the 2020 International Day of Light, I want to do a little explainer for how you can paint with polarization, and in particular, how you can find wave plates around the house and polarizers around the house to create nice and bright images. First, the monitor itself of any LED screen is a polarized light box. So this monitor is horizontally polarized, and you can use polarized sunglasses to see that you can cross the polarization. Regular transparent tape is birefringent, so it can act as a wave plate. In this case, the tape's optical axis is at 45 degrees. Our eyes are not sensitive to polarization, so you can't see that, but you can see it when looked through a polarizer. Here's a film polarizer that you can get, and you can see that the screen is mostly blank. Now
I did cover this. Let me skip some of this and see if near the end is the part I wanted.
all kinds of colors. You can create some very bright and interesting colors with interesting effects. Here's a play on the standard CMY, cyan, magenta, and yellow arrangement that you might be familiar with. But notice how, unlike normal additive color, in this case, cyan and yellow somehow add to give blue. This is very counterintuitive, and with painting with polarization, you can get all kinds of color combinations that you normally wouldn't get. What we have here in the corners is an arrangement of layered tape at 45 degrees in this case to show you the full palettes. These two top layers are the same tape arranged at 90 degrees to each other, where this is 1 layer, 2 layers, 3 layers, 4 layers, and such. 1 layer, 2 layers, 3 layers, 4 layers, and such. Here's an interesting reason why the intersection between cyan and yellow is blue. In this case, cyan is created by 4 layers of this tape in this orientation. But this yellow is created by 3 layers of this tape in this orientation. 2 wave plates, the same wave plate at 45 degrees will actually annul itself. So you have 4 layers this way minus 3 layers this way, and that leaves 1 layer in that direction, which happens to be blue, and that's why the intersection is blue. So painting with polarization is completely different than painting with other forms of light. You can have open polarizers where the polarizer of the screen is the same as this observation polarizer or analyzer, or you can have cross polarizers. And in this case, the cross polarization colors are complementary. This cyan becomes magenta and so forth, and you have a complete different arrangement of polarizations. And so by creating the various layers of tape, you can create the entire palette where you can make deterministic colors. For the 2020 International.
Okay, that was for the International Day of Light. That was in May this year. Nobody saw the video because I never released it. So happy International Day of Light, everyone. Okay. So I was mentioning that I was interested in moving to deterministic colors. And so what I did is I got about 12 different types of Scotch tape. Some are Scotch, that's a brand of 3M, which happens to be my favorite company in the world. But some are not. They're Seal It, they're duct tape, they're Grandin Toy. Some are, a lot of these are packaging tapes like the one that I was showing before that I just cut lengthwise so that they would fit. And what you're seeing is the careful layering of each one of those so that I can get a palette that I know any one of these colors now I can create. Now, in some way, so for example, if I want the hunter green, this hunter green, I don't know if you can see my arrow, but I can use the Grandin Toy premium packaging. I put it at this angle, which isn't quite at 45 degrees. It's a few degrees off from 45 degrees. But if I layer 4 of them, I can get that hunter green. I would point out, if you're trying to do this yourself, you will really quickly learn it's not that easy to layer tape, cut it to shape, peel it off, and put it exactly where you want. And while putting it there, not changing the orientation in any way. But this palette gave me basically it is like an artist palette. One of the differences between an artist palette and this palette, well, maybe it's not a difference. My father-in-law was over this weekend and I was telling him about this, and he said, oh, the difference between an artist palette and your palette is the artist can mix blue and yellow to make green, and you don't know what to mix with what to make any other color. And so I was pointing out that that's what expertise is. The artist palette isn't what gives them the color green necessarily. It's the knowledge of, if I mix X with Y, what will I get? This just happens to have slightly, this way of painting with polarization happens to be a slightly different approach. And so it's going to take me probably years to learn how to mix and match from within my palette to create hues. But that's just a different kind of expertise. The palette itself is still the basis of what you're working with. So this is the palette. And and I can have the palette in open polarization or in cross polarization. So here's both of them, but I can't mix and match between them. I can't take a color from the open and a color from the closed, because they're only observable when you change the polarizer. So this is what I had to work with. One of the very first things I did is I looked at some of the art that I liked, and I thought to myself, how close can I get to replicating it with my medium, with my paints? So this is Tom Clement, who's a contemporary artist from Ireland right now. I really like his work. I find it's geometric and really colorful, kind of simplistic until you try to do it yourself, even with paint, and realize how much soul this piece of art has. And I can prove that it has soul because this is my attempt at reproducing it. Now, 2 things to point out. One, I find absolutely no soul in my piece. It is completely lacking everything that makes the first piece artistic in any way. Secondly, I did a pretty good job of reproducing certain things with packing tape. Basically, this blue here is basically the same as that blue here. There's some greens here that change, and kind of here, shadow's impossible. I did not do a good job with this shadow here because getting a darker green is not that easy. I could get a different green, or in this case, I chose to go with gray. So this was one of my first attempts. Also, one of the things you'll notice right away is all of the mess in my sky. And also, these hatch marks right here. And the reason is, the piece of tape is at a fixed thickness. If you need to make a sky by patching up piece of tape after piece of tape, if the tape is not overlapping, if there's any gap, then you get white because the screen gets through. If there's any overlap, then you get a completely different color. So that's one of the things that has taken a lot of effort to get is to layer the tape in such that they're neither overlapped nor is there a gap. But anyway, this was my first attempt. I was very proud of it because it's the first example I know out there of deterministic painting with polarization rather than the random stained glass. I happen to love propaganda art from the turn of the last century. This here is on the left is a famous piece of Soviet propaganda art by Lidsky. It's got one of the best titles ever for representational abstract art called Beat the Whites with the Red Wedge being communism, of course, and the whites being the Tsarists. This piece of art is bonkers. It's from 1920. It was really the beginning of this kind of geometric non-represent or representational abstract art. So I was inspired by this, and I thought, oh, can I do something kind of similar? I don't want it to be the same. So the one you see on the right is my take. It's titled Apolitical Polarization, and really just having fun and getting the black and the white was the challenge here, and that was really fun to do, because instead of colors, you know, the white you can see actually the stripes in the white, but no stripes in the black. And so what's actually happening here is that the white is layered tape that oriented the screen, and the black is actually empty space. The black is just the glass that's through cross polarizers. So it's kind of the opposite than you might expect. And as you can see, you can still see those stripes, because it's very difficult to align pieces of sticky Scotch tape. You put it down wrong the first time, you might as well put another piece, because you can't pull it up and keep it clean again. So this was among my second attempts. And then of course, after Litsky, I started thinking about one of my very favorite artists from that time, Kandinsky. And so I started playing with some Kandinsky. I have a video that, by the way, that just shows what this looks like. Again, with and without the polarizers, because one of the exciting things about painting with polarization is this sense of magic. So for example, when you're making the art, you can't see the colors. You're kind of doing it blindly with transparent tape, and then you need to put the polarizer there to be able to see what you just made. And so that's both a hindrance, but also gives the opportunity of observing the art, you know, from going from transparent to suddenly colored. And then I have another video that shows another maybe bug as a feature about how, because the thickness of the tape matters so much and the alignment matters so much, viewing these pieces from slightly different angles gives a completely different color palette. So also it's both dynamic, but that interrupts the idea of having a deterministic color that you want. So this is the piece of art just on the screen. That's what it looks like without an analyzer. And then once you put an analyzer, you get all of the colors. And this is what it looks like, how it shimmers from all different directions. If you look at one particular thing, so let's take a look, for example, at these. I would say pay attention right here to these two semicircle arrangements. You'll see I made them such that the blue and the pink are inverted, you know, in the two. That was by design. I was aiming for blue and pink in this case. And here they are, green and green, and watch the blue and pink change, or the green and green change as you change viewing angle. And all of the other objects in this image are changing at different viewing angles. So it gives some opportunity for art in some ways that's, you know, looks completely different from the viewing angle that you're on. Imagine this being in some room and people are seeing it from different parts. They're gathered together and everybody's experiencing this slightly differently because it's got different colors. Now, I'm saying that's a bug as a feature. Other people might say, well, that's a real hindrance with creating art because I want to create a shared experience. I want to create a pad experience. And some artists feel that that's the point, and other artists feel that in fact that's a hindrance to art. So I find philosophically this question very interesting. Is it net value or net hindrance that the colors change based on viewing angle, and the contrast changes based on viewing angle. Okay, so this is what it looks like. This is what it's based on. So on the left is one of my very favorite pieces of art, Several Circles by Kandinsky. One of the things that Kandinsky does that gives his art soul, in my opinion, is not only is he working with these sharp circles that have interesting contrasting colors, but that there is some non-sharp, this corona around the main circle that's you know, white and gray, these blacks that are bleeding into grays. They're what makes this analog in some ways, and makes it really gives it the soul. In fact, I think that this corona here is what gives the sharp contrast of the inner circle such pop. Anyway, I tried not so much reproducing this art, but being inspired by it. And the hardest thing was trying to see if we could maintain some sense of this corona. And I'm very happy about this piece. This is probably my favorite piece that I've made. It really shows the dynamic color palette that you can get with the tape. All of the colors here are deterministic, meaning they were sketched out in advance. Whether or not I got the color I was aiming for is different, meaning maybe I meant for the pink to be redder, and the, you know, this tan here maybe was meant to be yellower, but now comes out a little golden. But I think this works really quite well. And I can guarantee you that, well, I can't guarantee you, but I suspect that nobody in history has painted with Scotch tape and no paint, right? You take away the polarizer, this just looks like a plate with a bunch of tape on it. Okay, this is another one inspired by, this is inspired by Kandinsky's aesthetic, although this doesn't, I don't have a piece to match this to, because this is my own piece entirely. It's not actually reproducing anything, but it's definitely inspired again by that era. This one's called Even Flow for all of you Pearl Jam fans. I really like this, this piece here. Then I started making some of entirely my own. This is Eclipse 2. And what you're seeing here is it being mounted in a frame on a window. So no monitor as the light source. This is just sunlight as the light source. And what you're seeing on the window is a piece of 8.5 by 11 printer paper is behind to give diffuse light from the incoming light, so it doesn't, so that you can't see the houses behind, for example. It diffuses the light. Then there's a polarizer there that polarizes the light. Then there's the piece of art on a glass plate. Then there's a final polarizer, and they're all in a picture frame where the backing has been taken off. So what you're seeing is the transmitted light from outside. And as you can imagine, at different times of the day, this looks very different. If it's not a bright day outside, maybe it doesn't look like anything. At night, it just looks like a piece of glass with some schmutz on it, like it just like some dirt on it, you know. And then you know, the sunlight comes up and it's extremely bright. So this is Eclipse 2. I also have Eclipse 1, which I like. So I've been exploring recently with framing these and what opportunities there are for framing. And I'm not there yet. I'm not particularly satisfied with something that needs to be glued onto a window. But I suppose it could be hung in a window, or a light box could be created for it, so it could be displayed anywhere. Okay, that's pretty much all I have. One thing I did want to point out is that I'm studying this phenomena from two aspects. During quarantine, or during isolation, I was interested in the artistic aspects. I wanted to see what I could make. Could I reproduce shapes and colors? You know, what are some of the technical, like it's very technical art. It's not really free flowing. I wanted to explore that. But then because I hit a limit of what colors I could produce, I got very interested in the physics of this tape, in actually measuring the birefringence from a physics standpoint, like how much difference in index of refraction there is, and all kinds of complicated things that, again, you wouldn't hear about until one of our senior optics courses. And so I have a spectrometer at home, and I've been working with a high school student in the lab to measure this stuff. And so really just working to measure what the tape is doing. And I mention this because one of the interesting things is that the tape isn't doing something, it isn't acting in an orderly manner like we would expect, where, for example, let's say I see red. Normally, the way we think of the color red is in terms of what we would call a spectral color. So what is a spectral color? Well, you know, here's the visible spectrum in terms of wavelength. Light has a wavelength. Usually it's measured in nanometers. We say the visible spectrum goes from 400 nanometers to 700 nanometers. And red is somewhere between 650 and 700 nanometers. So if I said to a colleague, you know, I have red light, you know, I put a piece of tape and I get red light coming through the cross polarizers, what would you expect is coming out? That colleague is likely to say, oh, if you were to measure it with a spectrometer, if you were to measure the what's actually coming out, you would get some small range of wavelengths of light. You get a peak of spectrum that would be somewhere between 650 and 700. And likewise, if I you know, saw some green, you would expect there, if it was a spectral color, that it would be a peak at 550. But in reality, the hues that you get from the tape have to do with a very careful elimination and suppression of certain wavelengths and other wavelengths. And as you layer the tape, different wavelengths shift up and down. And so a lot of the colors that you were seeing are these kind of non-spectral colors that our brain puts together, in the same way that one of the things that light, like physicists who study light, always make sure to distinguish is purple from violet. You might have heard this before, where violet is on the spectrum. It's around 400 nanometers, maybe 450, but purple, you'll hear somebody always insinuating themselves into your conversation and saying, purple's a non-spectral color. It's called violet. The rainbow has violet. The rainbow doesn't have purple. And the reason is because violet is actually a very specific color of light, and it is something that's coming off at 400 nanometers. But purple is a blue and a red that are both hitting our eyes. So let's say there's a peak of 450 nanometer light and a peak of 670 nanometer light, and both of those are coming into our eyes at the same time. We're actually seeing blue and red at the same time, but if they're on the same spot, our brain doesn't see it as a blue spot overlaid with a red spot. It sees it as what we call purple. And it looks very much to us like some light that comes off at 400 nanometers. So if I were to shine light that's perfectly just 400 nanometer light, you'd say, oh, that's purple. And if I were to just shine light that's 450 plus 675, two light sources on you, you'd say, oh, that's purple. And the difference is, one is a spectral color because it's a single wavelength or range of wavelengths, and the other is a perception color. Your brain interprets it to look like that. And so in the palette of colors from the tape, almost exclusively, they're all perception colors. Every one of those colors that you see has a whole bunch of other things happening. What's happening is the polarization gate is removing a little bit of some colors, and your mind sees golden from that. And then another layer of tape simply removes slightly other colors that are next to it and brings up those colors that it removed before. And then you say, oh, that's pink, you know, and so forth. So I'm currently studying with a spectrometer and with the tape, the actual colors that you get, the wavelengths that you get out through the tape, so that eventually I can have a scientific theory for predicting what colors I would get from what tapes. So the idea, right, the idea of science is to be able to make testable predictions. Otherwise, there's no scientific theory. So right now, I'm working to study the birefringence of a whole bunch of tape, such that you could give me any tape I haven't seen before, and if you tell me the birefringence of it, I can predict to you what colors it will demonstrate, it will give me. And that prediction won't be necessarily that easy to make, because it will be based on a fairly careful study of all of the suppressed colors in all of the tapes that I've had. So that's pretty much what I have. I just want to leave you with this. Yeah, you can do this too, especially the art part. You can play with this. There's you know, all kinds of things that you can do. First of all of your screens, whether it's your cell phone or your desktop monitor or your laptop monitor, they're all polarization light boxes. If you open some Word document or some PowerPoint document and leave it on white, then that screen is putting out polarized white light. If to be able to observe the colors that you make, you need another polarizer as an analyzer, and you can buy polarized film. It's called Polaroid film, but it's not the same as film that you get from a Polaroid camera. You can buy it. It's probably cost you a few tens of dollars to get some sheets, or you just use sunglasses. Your sunglasses are a Polaroid, and you can simply wear the sunglasses or rotate your head, and you will see the colors that happen between cross polarization. You can also film with your camera through the sunglasses. Just put your sunglasses in front of the webcam or the camera on your cell phone, and it will be as if you have a polarizer in between. Almost all transparent tape is birefringent. I really find that the standard Scotch packing tape is really quite good. It gives a dynamic palette. Also, Scotch transparent tape works, and it works at different angles from the packing tape. So if you have some Scotch transparent tape, like gift wrap tape, for example, and you have Scotch packing tape, with those two tapes, you should be able to create all kinds of stained glass and deterministic art. And I used to do this by putting the tape on the monitor or on a piece of transparency film. You know what works the best? If you go to a dollar store, you can buy picture frames, 8x10s or even bigger, or 4x6s. They're $2 or $1 for picture frame. Unfortunately, I throw out all of it except for the piece of glass. If you went to a glass store to buy glass, it'd be about $10 a piece. I think I was able to buy 3 frames for $2. And so then you have a piece of glass, and you can use that glass as your substrate for layering tape, for cutting on it, for creating. Basically, the glass is your canvas. You can get them from the $2 store. I would like to say to all of you, and there's about 50 of you on the call and several of you watching later, I'm dying to see what you guys make if you make something. So anything you make that you're proud of, or just think looks like cool, or maybe, maybe it does evoke some emotion in you. Maybe you can get to the art part that I think I was getting to by the end, but certain wasn't getting to the beginning. Send me pics by email. I suppose you can send it to me by Twitter. You can find me there too. But I would love to see what you guys make, if you make it. If you're too embarrassed to show Jessica, just send it to me. If you want Jessica to see it, send it to her and tell her that she's allowed to send it to me. I would love to see, you know, what you guys can do. And please, you know, you should be aware that you're among the first people in the world to see this. So you got a head start on a lot of people in learning how some of this works. And so you can go ahead and play with this. And if you put it on your social media or anywhere else, you'll be among the first in your peer group to have even looked at this from an artistic standpoint. Thank you, everyone.